Hello students, this is our third lecture with storage architectures. For the past two lectures, we have looked at the working of a single flash memory cell and how they are arranged as strings, pages, arrays, blocks, and lanes, eventually as dice, and how the SSD controller views them as channels and banks. In the next couple of lectures, we are going to dive into various functions of the SSD controller. For better understanding, I'm grouping these functionalities, and let's look at those groups first. The first one is reliability and maintenance features. Second are related to security of the data. The third feature is related to performance. Apart from this, there are few other activities that the SSD controller needs to perform. When it comes to the reliability and maintenance features, as listed here, the very first thing that the SSD controller needs to do is address mapping. Specifically, it's called flash translation layer, wherein the address from the host system is mapped to the actual DRAM devices. Second task is ware leveling. Third is garbage collection. In some contexts, all these three together are called as FTL. The fourth one is over provisioning. The fifth and sixth are more for reliable working of the flash memory cells. They are read and program disturb and write about features. The seventh one is error checking and correction. Eighth is a smart feature in some of the high-end SSDs. The ninth is defect management, how the SSD controller keeps track and handles flash cell failures. And the 10th feature is RAID. Write feature is not specific to SSDs, but it has been there even in the traditional storage systems. Following that, there will be most likely an encryption and decryption engine, a separate hardware for protection of data. When it comes to the performance aspect, just like we have the regular memory hierarchy of registers, multiple levels of cache followed by DRAM and then the secondary memory. Within the secondary memory, we can have a cache. This cache is DRAM based, primarily to give faster accesses to the host. Apart from this, there might be other activities to handle like communication with the host and the NAND chips, apart from other miscellaneous IO operations. To manage all these activities, the SSD controller will have a CPU in, in it. So this CPU is not so high end like the ones we usually study at the processor level. This can be a simple RISC processor. So in a way, you can imagine the SSD itself to be an embedded system that manages the communication and also handles various activities pertaining to the flash memory cells. So let's look at each of those features a little more in detail. The very first one is flash translation layer. The primary task of this FTL is, I'm sorry, the primary task of FTL is to map the logical address from the host to the physical block address in the NAND flash. So here, for example, the if we have 6 logical blocks with addresses 1, 2, 3, 4, 5, 6, one the block with address 1 can be mapped to a physical block with address A. Block 2 is mapped to B. Block 3 is mapped to E, so on and so forth. This mapping is primarily dictated by how the physical block usages has been. These blocks A to F. The mapping can be done at block level or page level, or can be a combination of both of them, or can be a sub page level. There are multiple design choices that people have explored. Unlike the SRAM and DRAM, the mapping that is done by the SSD controller is not so trivial. The reason being, first, flash memory has a unique requirement that before you can write a data to a cell, you need to erase it. It's called erase before write requirement. Also, as you already know, erase can be done at block level while write can be done at page level. So because of these two requirements of the flash memory, the FTL layer in the SSD controller needs to carefully track and manage the underlying memory blocks and pages within them. Where leveling is tightly coupled with the FTL, because flash memory cells have limited endurance, they wear out with usage over a period of time. Ideally, what we would expect is all the flash memory cells would wear out more or less equally. For example, if we have a logical block with 256 KB size, it would have 64 4 kilobyte pages. Now, if the number of writes to each of these pages are more or less same, then the endurance cycles per page for all the pages will be more or less in the same range. So the way we can interpret is all of them are dying more or less equally. But the reality is the writes of, of data is not uniform across pages. So here is an example of the worst case scenario where in this logical block almost all the writes were done only to the first couple of pages, page 0 and 1. In such cases, page 0 and 1 among the 64 pages will die out sooner or very fast when compared to others. So eventually this particular block will have only 62 pages within it. So in order to handle such realistic scenarios, the SSD controller applies wear leveling. What it basically does is it spreads out the writes to different physical NAND blocks and pages. For example, if this is our logical block, we have, let's say, 3 pages, green, blue and red. They can be mapped to the physical block this way, wherein if we look at the FTL, we will see that page 0 has been mapped to page 12, which is the green one. Page 1 is mapped to 18, the blue page, and page 2 is mapped to page 3 of the physical block. So this mapping is basically done by identifying the number of reads each of these pages has undergone so far, and those pages with minimum number of endurance cycles will be picked and mapped to. Eventually the data will be returned to them. Along with wear leveling and the FTL management, the SSD controller needs to do another closely related activity which is called garbage collection. This is mainly because of the erase before write requirement. Even if the controller wants to write only a page of data in a block, it cannot, because the block needs to be erased before this page can be written to. So the controller, instead of erasing the block at that moment, will pick some other free page in the block and write the data to it. The previous page where the data was mapped to will be marked as invalid. So over a period of time, there will be few set of pages with invalid status, few set of pages with valid data, so on and so forth. Herein, the garbage collection kicks in. It keeps track of all these invalid pages and reclaims them and makes them available for the SSD controller for the future use. So over past few years, many different garbage collection algorithms have been studied by the designers. They vary in their efficiency, reliability, and performance aspects. So a closely related metric with the garbage collection activity is write amplification. It is defined as the total number of writes to the flash cells upon the total number of writes sent by the host. Ideally, we would expect that every time the host writes data, we'll write it only once to the flash. But because of the erase before write requirement and eventual garbage collection, we might end up writing the same data more than once. So if the write amplification factor is higher, it means that our flash cells have experienced more number of writes or erase cycles. So it's a bad metric to, a bad number to be having higher. We need to minimize it as much as possible. So let's look at a couple of examples of how the garbage collection would work. Let's say here we have a page, and a set of 8 such pages is our data block. Now let's say we have received the first write from the host. So the SSD controller, say it picked the first page of this data block and mapped the logical block address which we received from the host, let's say it's 6, to this particular physical page. The remaining pages continue to be in the free state available to the SSD controller. Let's say the host has given a second write to the same page. Now because we cannot overwrite the first page, the SSD controller picks the second one, which is the immediate free page available to it, and writes the data. The first page will become invalid now, and the remaining pages continue in the free state. Eventually, let's say at the 8th write, the status of the data block would be something like this. The first 7 pages would be invalid state, and 8th block will be having the current updated value, or 8th page will have the current updated data. At this point, even though we have capacity to store 8 pages of data, 7 of them are in invalid state. Now the garbage collector kicks in and it picks a spare block or unused block available in the NAND chip, and what it does is it moves the last updated value to this new block, and it erases the previous block. At this point of time, if we look at the capacity of the SSD, we have 1 page of data, updated version, and we have 7 more pages for the SSD controller to use. This was not the case at this point. Even though we had capacity of 8 pages, we were using only, or we were able to use only 1 page. So the garbage collector frees up the invalid pages and moves the updated data to a new block so that the old block completely becomes free. So another quick example, let's say we have two blocks, block 1 and 2 of 128 kilobyte size, and let's say our pages are 4 kilobyte. So each of these blocks have 64 pages in them, marked as the green squares here, with E saying that they are available for the SSD controller to write. Now let's say the host has written 10 pages of data. So the SSD controller has picked the first 10 physical pages to write these addresses or to write this updated data from the host. Now let's say the host has again updated the same 10 pages. Just like the previous example, we cannot reuse the first 10 pages. So the SSD controller picks the next 10 free pages, which are 11 to 20 here, and writes to them, and the first 10 pages are in invalid or dirty status. Eventually, if the host has utilized the remaining 12 pages in this block 1, so this would be the status, wherein in block 1, even though we have I'm sorry, I think we have only 32 pages here, not 64. So among the 32 pages here, 22 are being used effectively, the remaining 10 are underutilized. The garbage collector now kicks in and moves the valid data to a new block, and the old block is erased. Now if you look at the total capacity available to the SSD controller, we have 10 pages of block 2 and 32 pages of block 1 for any future data or update. So this way effectively the garbage collection happens, and it helps the SSD controller to better utilize the available NAND cells. What we have observed so far is when the host is updating the data. Now what happens if the host has deleted a file? Typically the operating system updates its directory saying that some particular file has been deleted, and it doesn't usually send an erase command, explicit erase command to the SSD. But with the current scenario, just the file structure has been updated, but the actual file data is still residing in the SSD. So it has two side effects. One is the effective storage space is not freed up. The second is it can be a potential security issue wherein an unauthorized person can retrieve this particular file and its information. So in order to avoid that, the OS upon a permanent file deletion will send an explicit trim command to the SSD. The SSD on receiving this trim command for along with the file addresses, it marks all the physical blocks across all the physical pages across all the blocks to be in dirty or invalid state, and a file's data can be in multiple locations, so the SSD does an exhaustive search. SSD controller does an exhaustive search and marks all of them to be in invalid state. All these blocks are later reclaimed by the garbage collector and made available to the controller. So these are the first three tasks of the controller: FTL, flash translation layer, followed by wear leveling and garbage collection. Another feature of the SSD controller is to handle over provisioning of the flash memory. Usually when an SSD is purchased, the actual physical space that's on the SSD is much higher than what's visible to the OS. Typically 7 to 8% of capacity is over provisioned, and for high-end SSDs it's almost 28%. So what it means is, let's say if the SSD size is 512 gigabyte, its actual capacity is nearly 550 gigabyte, but only 512 of that can be used at any given point of time. So the difference of 7.3% is over provisioning, and this over provisioned space is used by the controller for bad block management or defect management, for wear leavening, garbage collection, and to store firmware which need not be explicitly under the control of the OS, host OS, and also some spare sectors or blocks for any future usage. So the pros of such over provisioning is that the controller can use it for improving the overall lifespan of the SSD, reduce the write amplification aspect, and also it can improve the performance by trying to achieve multiple parallel transfers simultaneously. On the flip side, as you already realized, out of 512 GB, out of 550 GB, we are able to use only 512 GB at any given time. So as an end user, we are losing the storage space. For high-end SSDs, because of all these managerial aspects that the SSD controller cannot sacrifice, there is a higher ratio of over provisioning. So whatever we have discussed so far are more or less the managerial aspect or maintenance aspects of the controller. Now we will look at a couple of reliability aspects. These are primarily because of the underlying working of the flash memory cells. A typical read or program operations on flash memory cells can potentially disturb the data stored in the neighboring cells or the adjacent cells to them. The reason being, for reads, in order to deselect the neighbors, a high bias voltage is applied. Because of that, the data in them or the data in the floating gate as electrons can get disturbed. For programming the flash memory cell, a very high voltage is applied at the control gate. Because of this, the neighboring cells can get affected and their data can get disturbed. So the impact of such high voltages has been increasing over time because of technology scaling. The flash memory cells have shrunk in size, so they are becoming more and more susceptible to these voltage differences. Also, these read and program disturb scenarios are much higher in MLC and TLC scenarios, wherein we need much tighter control of the number of electrons present in the floating gate. They are much more sensitive than SLC cells. Also, even if we tend to read the same set of cells time and again with high frequency, it can result in disturbance of its neighboring cells. So an abstract representation of how the read disturb can look like: if we are trying to read this page, the page just beside it can have an high voltage to it, mainly to deselect it, so its cells can get disturbed. Also, there can be a page which is right at the end of such an array, wherein we read out the data from this array. So both these set of cells are will experience high disturbances. Now this is a case for program disturb. Let's say we are programming the two cells in blue color. All the adjacent cells will experience a high voltage disturbance, mainly because the the cells to which we need to write the data will be having a high voltage at the control gate, and the remaining will be deselected, again because of the potential difference. The data in the form of electrons stored in the floating gate can get affected. So to minimize these disturbances, the controller in general keeps a count of how many reads and programs have happened per page. If this number reaches a predefined threshold, it means that that particular page has been used reasonable number of times. It performs where leveling. What it means is this particular page can be moved to some other page physically, so that the disturbance that has happened so far in the adjacent cells can be minimized. Also, the controller can employ ECC to certain effect to correct few bit errors because of the disturbances. But beyond a limit, again, we still need to go back to the where leveling method. So these are the two precautions that the controller needs to take to reduce the overall read and program disturbances in the adjacent or neighboring cells. Another reliability aspect with the flash memory cells is upon a power failure, if we are performing a write to the NAND cells, what will happen to the data? Usually the data will be lost, but in addition, there can be a firmware related data and internal some other metadata that can get corrupted. So usually the high end SSDs are equipped with a sudden voltage drop detection circuit, and upon detection they will be disconnecting the external power supply, and they can have an internal power backup within themselves which will come into the uh, operation. Once such sudden voltage drop has been detected, the same circuit will trigger the write abort circuitry. This write abort circuit can do one of the following actions. For the data to be that has been returned to the host and which is not updated in the flash yet, it means that it is residing in the disk cache. It can do two writes of the same logical block to two physical pages as a backup. If you remember, the redundancy will reduce the percentage of failure. So two blocks will have the same data. Whenever the next time it has been booted up, the controller merges these two physical blocks so that eventually only one physical block will be there. Or it can abort the write operations which are in early stages if the user is given an option, and if he chooses okay you can neglect the data, so the controller can abort all the writes that are pending. So this is a little risky and it definitely results in data loss. Also, it can Proactively, upon detection of sudden voltage drop, copy all the contents of the disk cache to the flash, and during this time the internal backup power will supply the required voltage for all the activities. Along with this, the SSD controller can have ECC and defect management. The controller performs error checking and correction for all the data transfers that have happened from the host to the NAND flash and the other way around. In order to speed up things, there will be a dedicated hardware which performs the error checking and correction. The effectiveness of such error checking and correction can be dependent on the type of mechanism that has been used. And for high-end SSDs, typically we can detect multiple errors and correct some of them. Apart from the ECC, the controller, as I've already mentioned, keeps track of all the bad or defective blocks, NAND blocks of memory, and these defective blocks are avoided for any usual mapping that is done at the flash translation layer, and these bad blocks are remapped to the spare blocks which are available as part of over provisioning. Apart from these, the many of the high-end SSD controllers are equipped with a smart feature, expands to self-monitoring, analysis, and reporting technology. It's not available in all the SSDs in the market. What this smart feature does is all the activities done by the SSD are monitored and logged, and when the host system requests, all the statistics will be given to the host. For example, the smart feature can give an idea to the host system on the remaining lifetime of various NAND blocks based on their usage statistics. Also, this smart feature can help the host in case of any failure or data loss scenarios. So when it comes to the security features of the SSD controller, it can have a dedicated hardware performing the encryption and decryption of the data. We need a dedicated hardware primarily to reduce its impacts on performance. This dedicated hardware or engine encrypts the data before it writes the data to the flash and decrypts the data whenever the host is requesting for it. And like I mentioned, it happens in parallel with because of this exclusive hardware, so that eventually the host need not actually experience any delay with the data transfer. One of the most popular encryption method is AES 256-bit, which has been more or less a standard of late. So with that, I'll pause this lecture. We'll continue looking at the other SSD functionalities in the coming lectures. Thank you.